This is the second lecture on Hamiltonian mechanics. In the earlier class, we have introduced the, the Legendre transformation and differentiated between active and passive variables. The passive variables does not undergo any change due to Legendre transformation. And by Legendre transformation, we transform a function or few variables of a function by their conjugate variables, and the original function and the transformed function have the same physical dimension. Today we shall start the Hamiltonian dynamics proper. We have mentioned several times that there are different formalisms of classical mechanics. Let us first see what we do in Newtonian mechanics. In Newtonian mechanics, we write the equation of motion in terms of forces and the accelerations, and thereby solving the equation of motion, which is a second order differential equation in time, we directly get the particle trajectory. The problem lying or the difficulties that we encounter in Newtonian mechanics is that it is in the vector form equation. So if we want to add more than one forces, they are to be added vectorically. This is one problem. Secondly, since the equation is in vector form, the form of the equation changes from one coordinate system to another coordinate system. The main problem is that Newton's laws of motion are valid only in inertial frames. In non-inertial frames, pseudo forces are to be incorporated in the formula F. The inclusion of the forces of constraint is a bit cumbersome in Newtonian mechanics. These are overcome in Lagrangian mechanics. Lagrangian mechanics the form of Lagrangian mechanics is invariant, or equation of motion of Lagrangian mechanics is invariant under coordinate transformation. The equation, we get the equation by solving second order differential equation. If we have a system with n degrees of freedom, then we have to solve in second order differential equation. By solving this, we get q's, which are the generalized coordinates, and this does not directly give us the particle trajectories. To get particle trajectories, we have to back transform the generalized coordinates into position vectors so that we get the particle trajectories. This is the big difficulty we encountered in connection with Lagrangian mechanics. And the Lagrangian, we can include the effect of non-inertial frame in Lagrangian mechanics very conveniently, that we have discussed, and the formalism can well be used to charge particles subjected to electromagnetic field. The Hamiltonian dynamics is another alternative formalism. In Lagrangian mechanics, we are to solve in second order differential equation. In Hamiltonian dynamics, what we do, we deform the mechanics in such a way that instead of solving in second order differential equation, we are to solve 2n first order differential equations. So again, the number of initial conditions that have to be supplied still remains 2n. We change the variable suitably and using Legendre transformations, so that the second order we need not to solve second order differential equation. We are to solve only first order differential equation, whose number gets doubled compared to Lagrangian formalism. This is the fact lying with Hamiltonian dynamics. The Hamiltonian dynamics is mostly suitable when we make a transposition from classical mechanics to other modern theories of physics. Classical mechanics has a limited domain of application when we go into the small size systems, we want to go to quantum mechanics. The transition from classical to quantum mechanics is best performed through Hamiltonian formalism of classical mechanics. Similarly, when we use an aggregate of particles which interact with each other, none other than statistical mechanics is to be employed, and the statistical transition from classical to statistical mechanics is also mediated via Hamiltonian's form. Now we come to the Hamiltonian. In Lagrangian, the Lagrangian is a function of QIs, the set of QIs, QI dots, and of D. This is the Lagrangian. We want to replace these variables by the conjugate variables. So we define another function H, which is QI dot del L del QI dot minus L. So that I sum over I ranges from 1 to n. Note that originally in thermodynamics we generally use function g as f minus x del f del x by this form. But here we have defined function g as x del f del x minus f. The change in the sign is because that for conservative system H can be identified with the total energy of the mechanical system if we employ Lagrangian transformation in this form. If we put L minus this thing, then H comes out to be minus E. So this is just a matter of sign convention. And we know that from Lagrange's equation that this is nothing but P. So we define this as QI dot Pi minus L. I is equal to 1 to n. Now this is the Legendre transformation. If we write dH, then from this equation we get this is summation over I is equal to 1 to n. This is QI dot Pi plus Pi dQi dot. This is this part minus dl. As L is a function of this immediately gives that dl is equal to summation over I is equal to 1 to n del L del QI dQi plus del L del Q del L del QI dot dQi dot plus del L del D dt. Now for this part is Pi. So this is Pi QI dot and this is Pi dot dQi. This is dQi summation over I is equal to 1 to n plus del L del dt. We plug this into, so we get I is equal to 1 to n QI dot dPi plus Pi dQi dot from 1 this part minus Pi dot dQi minus Pi dQi dot minus del L del T dt. And you see that this part cancels out with this and leaving behind I is equal to 1 to n QI dot dPi minus Pi dot dQi From this equation, we readily get that del H del Pi, del H del Pi is equal to Qi dot, and del H del Qi is equal to minus Pi dot, and del H del T is equal to minus del L del T. These two equations, the first two equations, are known as Hamilton's canonical equation. Hamilton's equations. You recall one thing, what we did in the Lagrangian dynamics. In Lagrangian dynamics, we find that Pi is equal to del L del Qi, and Pi dot is equal to del L, sorry, Pi is del L del Qi dot, and Pi dot is equal to del L del Qi. In transforming from Lagrangian to Hamiltonian, we have obtained H is equal to this, which shows that H is a function of Qi, Pi, and T. Qi, Pi's, and T. So, as we move from here to there, Q and T are in passive variables. You recall that Pi dot is equal to del H del Qi. So it is the same definition that we have obtained in earlier. So the passive variables, this BQI being passive variable, we have obtained this relation. Recall that in the case of f of xy, we have u is equal to del f del x, v is equal to del f del v, del f del y, and if we define f1 is equal to f minus xu, then df1 was minus x du plus y dv, sorry, dvy, v dy, and from here this is df1, del f1 del u is equal to minus x, and del f1 del y is equal to v. So the definition of v was same in terms of original function and transform function. Here also you see that q being the passive variable, qi being the passive variable, the definition is same in respect of h and L. So this is the Hamilton's canonical equation. Another way of arriving at this equation is that starting from this equation, we know alternatively we know that h is a function of qi's, pi's, and of t. So we write dh, take the differential of this. So this is equal to summation over I is equal to 1 to n del h del qi dqi plus del h del pi dpi plus del h del t dt. If we compare this equation with this equation, since the coefficient of pi will be same, so del h del pi is qi dot, del h del pi is qi dot. This is this equation comparing the coefficients of Qy and t, we get the other two equations. So these are the Hamilton's canonical equations. These are there are n such equation and n such equation like this. So there are this original Euler-Lagrange equation, there were n equations, second order differential equation. These are replaced by 2n first order differential equation. These equations may be solved to get the information about the system. To proceed further, we first take few examples. Linear harmonic oscillator. We know that linear harmonic oscillator, the Lagrangian is half m x dot square minus potential energy half m omega square x square. So we define Px is equal to del L del x dot is equal to mx dot, which gives us x dot is equal to Px by m. And we define Hamiltonian. This is x dot Px minus L. This is the customary definition of H. Do not write H as T plus V, because this definition is valid only for conservative system. So now we replace the x dot. So this is x dot Px, so this is mx dot square, so this is mx dot square minus half mx dot square plus half m omega square x square. So this is altogether half mx dot square plus half m omega square x square, but this is not the Hamiltonian, because Hamiltonian is a function of x and px. So we are to replace x dot over here by px, so that this becomes px square by 2m plus half m omega square x square. So this is the Hamiltonian of the system. Now coming to Hamilton's canonical equation. Now let us have. So x dot is del H del Px with a plus sign. So this we get Px by m. This is the, we know the equation, and for Px dot, this is minus del H del x. So this Px dot del H del x. So this is m omega square x minus m omega square x. This is nothing but minus kx, the restoring force. So we get the same equation irrespective of the formalism we employ. Another example is the simple pendulum. Let us consider simple pendulum problem. Other problems we shall discuss in separate class. So for simple pendulum, simple planar pendulum, we know that the Lagrangian was half m L square theta dot square, and the potential energy was mgl theta. So p theta was del L del theta dot is equal to m L square theta dot, which also gives that theta dot is equal to p theta by m L square. Now the Hamiltonian is theta dot p theta minus L. So this becomes half ml square theta dot square plus mgl cos theta. And here again we replace theta dot by, so this is p theta square upon 2ml square. L cos theta. So theta dot is equal to del H del p theta is equal to p theta by ml square. This equation and this equation are the same. And p theta dot is equal to minus del H del theta. So this is equal to plus mgl sine theta. If we replace sine theta by theta, then we get the force, the restoring force that acts on the simple pendulum, which tries to bring it towards the equilibrium position. With this example, we now go to the further discussion on Hamiltonian. We consider a system, a conservative system. For a conservative system, we know that the potential energy does not depend on block. It is a function of coordinates only. So for conservative system, del V del Q I dot is equal to 0. So one thing is that we can write del L del Qi dot is basically del L Qi dot T minus B is equal to del T del Qi dot. Now the kinetic energy, T is the kinetic energy. P is kinetic energy, which is defined as half summation over K is equal to 1 to N, the number of particles, Mk Rk dot Rk dot, where the position vector Rk of the kth particle is actually a function of set of generalized coordinates and of time. So Rk dot, which is equal to Vk, can be written as summation over I is equal to 1 to N. This is degree of freedom. This is number of particles. Del Rk del Qi dot plus del Rk del T. So this expression becomes half summation over K is equal to 1 to N and summation over I and J is equal to 1 to small n. This is Mk. Then we have del Rk del Qi dot plus del Rk del T and another similar expression dot del Rk del Qj dot plus del RK del T. This can be written as half summation over K is equal to 1 to N summation over Ij then Mk del Rk del Qi dot del Rk del Qj Qi dot Uj dot plus summation over K is equal to 1 to N summation over I is equal to 1 to N Mk del Ri del Rk del Qi dot del Rk del T Qi dot plus summation over R summation over Mk K is equal to 1 to N del Rk del T dot del Rk del T, which we write as half summation over Mij Qi dot Qj dot plus summation over I Bi Qi dot plus C, where Mij is half summation over K is equal to 1 to N del Rk del Qi dot del Rk del Qj, and similarly Bi is equal to summation over K is equal to 1 to N del Rk del Qi dot del Rk del D, and C is equal to half summation over K is equal to 1 to N del Rk del T del Rk del T. If the transformation equation do not contain time explicitly, then this term becomes 0. So in which case this becomes 1 upon summation over Ij Mij Qi dot Qj dot if del Rk del T is equal to 0. So in which case the transformation equation do not contain time explicitly, so the kinetic energy is a quadratic function of generalized velocities. Qj dot. So now returning back to this becomes summation over J Mij Qj dot. Sorry, and so when you multiply this, sorry, this is sum over. So whenever we multiply this by del L del Qi times Qi dot, we did, what we get is sum over I, we get, this is because this is sum over j, we get sum over ij mij qi dot qj dot. This is nothing but twice t, because t was half of this t, so this becomes twice t, and in which case the Hamiltonian, which is the summation over qi dot del L del qi minus L, this becomes twice t minus v, so t plus v. So the Hamiltonian is equal to the total mechanical energy when the transformation equation does not involve time explicitly, and the system is a conservative one. So this is one of the major significance of the Hamiltonian. Other form is the Hamiltonian dynamics is found to be especially helpful when some of the coordinates are cyclic. We shall take up this consideration in the next class.